Instead of a mass on a spring oscillating back and forth, as we looked at in the previous video, let's take a look at a simple pendulum. Of course, by simple pendulum, I mean the string or the rod is massless. All the mass is in a point at the end of the string. And if we displace it from equilibrium, if we raise it up to some angle and let go, it's going to go back down towards its equilibrium position. Because it has inertia, it's going to pass right through its equilibrium position, and it's going to come to rest over here, and then it's going to swing back. And it's going to swing back and forth between those two positions. If we ignore air resistance, it would swing like that forever. So let's take a closer look at this. Let's start by drawing a free body diagram of our mass on a string. What's touching our mass? The string is. So we've got tension in that string. And what can reach in from a distance? Gravity. And that points towards the center of the earth. Once I draw this, I have to decide how to break up my vectors into components. What coordinate system do I use? And I know I have something moving in circular motion. There's radial acceleration keeping my object moving in a circular path. And there's tangential acceleration causing it to speed up and slow down. So I'm going to pick a coordinate system that has a radial component and a tangential component. The tension in my string is already pointing in the radial direction. I don't have to mess with that, but I have to break up my force of gravity into a component that's radial and a component that's tangential. And if we define this angle as theta, then this angle in here is also theta. So mg cosine theta is my adjacent side of my right triangle. This is the right triangle. The hypotenuse is mg. So mg cosine theta is the adjacent side, which is my radial component. And my tangential component is mg sine theta. So my tangential acceleration is going to be equal to the sum of the forces in that direction. And there's only one force in that direction. And it's opposite the direction of the displacement. If I pull this mass up and to the right, the force is back to the left. So if I write this as a vector equation, I really need a negative sign there to keep everything correct as far as directions are concerned. The mass cancels out. And now, in order to simplify this problem a little bit, we're going to make a small angle approximation. If theta is small, then the sine of theta is approximately equal to theta. Of course, we have to be in radians. But this is true. The sine of theta is approximately equal to theta in radians if our angle is small. And we can rewrite this equation as minus g theta equals our acceleration. And we know our acceleration is the second derivative of position. And so let's think about what's happening here. Our mass is moving in an arc length. We usually use s to show the distance of an arc length. So a would be equal to the second derivative of that with respect to time. We know the arc length is equal to r theta if we're in radians. So if we're in radians, this is true. Let's plug that back in. We've got minus g theta is the second derivative of r theta with respect to time. Remember, theta is a function of time, It changes with time. And so is s. S is also a function of time. It changes with time. The position of our particle along the arc length changes with time. So what does this tell us? It's the same equation we saw in the previous video with a mass on a spring. The only difference, our constant is a little bit different now. Before we got K over M. Now we have G over R. And what is R? R is the length of our string or our pendulum. So I'm going to change this to an L. The length of the string times our theta, which is really a function of time. It changes in time. Has to be the second derivative of that function with respect to time. So we take two derivatives. We get negative a constant times our function back. That means that a sine or cosine function will satisfy this requirement. So let's let theta be a cosine omega t plus phi. A is our maximum theta, our maximum angle that our pendulum is displaced from equilibrium. Omega is going to give us this constant out here, g over L. So we take two derivatives, we're going to get an omega squared. So omega squared has to equal g over L. G, the acceleration of gravity, L, the length of our pendulum. And phi is used to set the initial conditions. What is this pendulum doing at t equals 0? Is it at its maximum displacement at rest? Or is it moving through the equilibrium position with maximum speed? Or is it somewhere in between? So for a mass on a spring, we saw that omega, the angular frequency of our oscillating system, was the square root of k over m. K was the spring constant, m's the mass. For a simple pendulum, we now see that it's the square root of g over L. G is the acceleration of gravity. L is the length of our pendulum. And for a physical pendulum, you can do that also. And what you'll find is that omega is the square root of mgd over I. D is the distance from the pivot point to the center of mass. And I is the rotational inertia of the pendulum about the pivot point. Just to review, anytime our restoring force is proportional to the displacement, we get simple harmonic motion. That means the second derivative of our position as a function of time will give us negative a constant times our function again. So any sine or cosine function would work to describe that motion. And what is omega? Well, omega squared is equal to the constant that we get when we take two derivatives. Negative the constant times the original function. That constant is omega squared. And for a mass on a spring, it's the spring constant divided by the mass. For a simple pendulum, it's g over L. And for a physical pendulum, it's slightly different. There are other types of oscillating systems, and omega takes on slightly different forms for each of them. As long as the force is proportional to the displacement, we get simple harmonic motion.